Welcome to the 7th video, Physics Informed Machine Learning. At the end of last chapter, we hit an uncomfortable truth. We had finally built a model that respected how the grid is wired. And it still did not know a single law of physics. Watch what that means. A network trained only on data looks at one point on the grid and tells you with total confidence this much power flows in and that much power flows out. And has the two not match eventually? It can hand you a state of the grid that violates the conservation of energy itself. On a presentation slide, that is a rounding error. On a live grid, it is a model you cannot trust with anything that matters. What if the laws of physics were forbidden to break? For most of the series, our models have been black boxes. You point data, they find whatever pattern shrinks their error, judge on one thing: how close their predictions land to the examples they were trained on. That works beautifully when you have mountains of data and only ask about the past. But the grid is safety critical and it keeps doing things it has never done before. New renewable mixes, record breaking weather, faults nobody has seen, that can happen. So here's the fix, and it is elegant. Remember how a model actually learns in previous videos. It minimizes a loss, a single number that measures how wrong it is. Normally that loss measures just one thing, the gap between prediction and data. Now add a second term, a penalty for breaking the laws of physics. Take a governing equation, say power in must equal power out, and measure how badly the prediction violates it. The measure of violation is called physics residual. Add it straight into the loss. Now the model is punished two ways: for disagreeing with data and for disobeying physics. And that little factor in front of lambda is a dial. How much do we care about matching the data versus obeying the law? That's a big question. Turn the dial and the network learns to do both at once. So, when the governing law is a differential equation, which in physics it almost always is, that this idea has a name: Physics Informed Neural Network, a PINN. A landmark 2019 paper showed you could train a network using the equation itself as the teacher. The very next year, researchers at the Technical University of Denmark brought this into our world. They taught a network the swing equation, the law of whether generators stay spinning in sync. Their work won Best Paper at a major power system conference that year. And here's the beautiful payoff. Anchored to real physics, the model needs far less data. Push a pure black box past the edge of its training data and it drifts into nonsense. Push a PINN and the physics quietly holds it to a plausible answer. The equation becomes a guardrail. There is an even more practical flavor, and it is how a great deal of engineering already works. Do not ask the network to learn everything. Let your trusted first principles model do the part it does well. Then let machine learning handle only what those equations miss, the messy residue. The unmodeled friction, the sensor quirks, then the things physics is simply silent about, the white box of physics, the black box of learning, the grey box in between. This is the case. So why does any of this matter beyond being elegant? There are three reasons actually, and together they are why this chapter is really about one word: trust. First, data efficiency. Physics constraints mean you get away with far less data. Gold when real grid events are rare actually. Second, plausible outputs. The model will not hand you an answer that breaks conservation of energy, so even its mistakes stay physically sane. And third, the one that matters most here, explainability. When a regulator or tired operator at 3 in the morning asks, "Why should I believe this?" Then, because it cannot violate the law of physics, an answer they can accept. There are tools built for this: Deep XDE, NVIDIA's Modulus, among others. And the graph network we ended to last chapter. Researchers are already fusing the two, projecting the graph network's output back onto Kirchhoff laws, so it physically can't violate them. Honestly, none of these is free. These models are harder to train. That lambda dial balancing data against physics is amazing. Set it badly and the model learns harder. And you have to actually know the right equation. It's not like a silver bullet. But step back and look at what we have built. Classical learning, deep networks, generative AI models, agents that act, graphs, and now physics. So, 6 chapters of methods, genuine toolkit. We are actually coming to the end. So, we turn from how to what, predict in the future, we meet in forecasting. Thank you for hearing me out.